We have a very exciting demo for you today. This is called Dragon's Breath, where we can kind of make it look like we're breathing fire. Now this is pretty dangerous and we don't want to try this one at home, but my student has been safely trained in how to do this properly. So in front of you, you see a propane torch. It is lit. It's kind of hard to see the flame right now with the light behind it, but that's okay. And what my student is going to do in a second is he's going to blow some powder called lycopodium powder through the flame, and it will make it look like he's breathing fire. Lycopodium powder is a very fine yellow powder that actually comes from a plant, and the only reason that it's flammable is because of how tiny the particles are. So I'm going to have him go ahead and breathe this, and hopefully it'll look like he's breathing fire. Wow, wasn't that fantastic? We're going to try it one more time in the dark. And now we're in the dark. It's not fully dark in this room, but it's been darkened enough that you can actually see the flame. And now let's see what this dragon's breath looks like in the dark. Woo! Fantastic. We hope you enjoyed that demo. Again, please don't try this at home. Okay, we have an exciting demo for you today. We are going to burn a gummy bear in a salt called potassium chlorate. Now, the salt is not very reactive in the solid state. Instead, I'm going to have my student melt it by heating it up with a propane tank to get it really, really liquidy. And so you can hear the propane tank on. We're going to melt this salt, turn it into a liquid. The liquid is much more reactive than the solid, and so it's going to be better able to burn this gummy bear. Also, potassium chlorate has a lot of oxygen in it, and so that's what allows it to be so good at burning things. I think that looks pretty melted, so we're going to have him turn that propane tank off, and now my other student's going to add the gummy bear, and we'll see what happens. Whoa! Look at that amazing reaction. So much energy coming out of one gummy bear. That was really cool, and you might have seen that purplish color. That's from the potassium in the potassium chlorate salt. Really cool. We're going to come back and do one more version of this using a different salt and a different candy. Okay, we are back with a different salt that we are currently melting. This one is called sodium chlorate, so very similar to potassium, it just has sodium metal instead of potassium. And it looks like it's nearly melted, so I think I'm going to have my student take the heat off. And now we're going to add a different candy. This is a peanut M&M. Energy of that reaction and the different types of burning from the 3 layers of the peanut M&M. It's very exciting. Lots of energy found in those things. We hope you enjoyed these demos. Please don't try these at home. Okay, now we have an exciting demo. Not something you can try at home, but really fun to watch on video. We hope you enjoy what you're about to see. So on the left, you see this flask that has this clear, colorless liquid. It kind of looks like water. We're going to pour it into the second flask, and we should see it magically change. And now it kind of looks like a rosé wine. And now we're going to pour it into the third flask, and we're going to see it change again. And now it looks a bit like milk, or kind of a strawberry milk. And finally, we're going to pour it into the last flask, and we should see it change one last time into beer. Look at all that foam. How cool is that? So this is the water to wine to milk to beer demo, and of course we're not doing magic. Instead, we started with a solution on the left that contained a little bit of a base, and when we poured it into the second flask, there was an acid-base indicator that turned it pink. Then we poured it into the third flask, and it had a chemical in it that made it precipitate. That's the white milky stuff you see. And in the last flask we had some acid and some chemicals that are kind of orangey, and so when the acid and the original base mix, they make all this foam, and it's a really fun demo. We hope you enjoyed that. Okay, for this demo we are going to do something called chemiluminescence, which means a chemical reaction that gives off light. So I'm going to have my student pour the 2 liquids into a funnel that you probably can't see, but as he slowly starts to pour these 2 liquids into that funnel, they're going to start to react, and we'll start to see, look at that beautiful blue light that we see. So as these 2 chemicals react, they give off a blue light. Most chemical reactions give off heat when they react, but this one gives off light instead, and we get this beautiful blue light spiral because of the way we have our tubing set up. Again, this is called chemiluminescence. This is something similar to what happens in fireflies, except they call that bioluminescence because it's a biological reaction giving off light. Beautiful reaction, beautiful blue color. It doesn't last very long. Also, it's similar to glow sticks, but because glow sticks are all contained inside the plastic, they last a lot longer. This reaction is exposed to the air, so it kind of kills that reaction really fast. So that's why he has to keep pouring the chemicals for us to continue to get to see the blue light of this chemiluminescence reaction. Really cool, really fun. Can't try it at home, but you can play with glow sticks, so have fun. Okay, we have an exciting demo that we're going to do for you today, but this is not one you can try at home. We are going to try to make a nylon rope. In front of you, you see a watch glass. This watch glass has some sodium hydroxide solution and a chemical called hexane 1,6-diamine. It's kind of a longer molecule, but not really, really long. What we're going to add to it are some drops of adipoyl chloride mixed with hexane. And this molecule is going to react with the other one and to start making a polymer called nylon. And then once we've added enough drops, we're going to start to pull the interface between the two of them, and hopefully it will be making a nylon rope. Oh, there it goes. As you can see, it's starting to pull this nylon rope out. We continually add the drops of the adipoyl chloride, and we can continue to pull and make this nylon rope come out of this reaction. It's really cool. Nylon is a type of polymer. A polymer is a word for a very long chained molecule, and as you can see, we're making a very, very long chain here. And as long as we continue to add drops, we can continue to make this nylon longer and longer and longer. A really cool, fun experiment. Again, not something you can try at home because the chemicals are pretty dangerous, but in a safe, supervised environment, we can do this in the chemistry lab. We hope you enjoyed this one. Okay, my students here have made a really cool thing called a ferrofluid. So this is actually a magnetic fluid or liquid. What we have here is a bunch of homemade magnetite, and magnetite is a magnetic version of iron with oxygen in it, and underneath he is holding a bunch of really strong magnets, and those magnets are creating a magnetic field that actually makes the ferrofluid go up in spikes. You can kind of see these little spikes forming on the watch glass, and that's all the attraction to the magnetic field that's being generated by the magnets that are underneath it. So again, this is called a ferrofluid. It's kind of a tricky thing to make. You probably can't do it at home, but if you're a little bit older and you want to try, there are some really cool recipes on the internet to make your own ferrofluid at home. We hope you enjoyed this demo. Okay, we have an exciting demo for you now. This is something that you may have sort of done on 4th of July, maybe if you've ever made one of those black snakes. This is a chemical version of that. So in front of you, you see a beaker full of sugar, just regular sugar from the kitchen. My student's going to add something that you don't have at home, and please don't try this at home, but he's going to add a whole bunch of what we call concentrated sulfuric acid. So he's going to pour it in, and this is a very dangerous chemical. You would not want to try this at home, and it's very reactive with the sugar. The sulfuric acid has a lot of oxygen in it. The sugar actually has a lot of oxygen in it too. And so they're going to start to react, and it's actually going to burn the sugar, turn it into carbon. And we're also going to see lots of heat given off. And basically this is a type of what we call a combustion reaction, where we're generating a lot of heat. And it's a type of burning reaction. So you can see that the sugar's already starting to burn a little bit. It's almost caramelizing. We would not want to eat this, right? But that's the process of caramelizing, is technically you're burning the sugar a little bit. This is a chemical burn of the sugar, so it's a little bit different. This does take some time, so we're going to have some patience as we watch him stir that concentrated sulfuric acid into that granulated sugar. So with patience, we will eventually start to see some changes. You can actually see some changes that have happened already. It's gotten much darker compared to how it began when it was completely white, and now it's very, very dark brown, almost black. So we are slowly turning it into that jet black color of charcoal. My student is done stirring, so now we're just going to let it sit, and hopefully we'll get to see some cool stuff start to happen. Oh, there's some bubbling. Oh, look. Can you all see the carbon snake growing? Look at all the smoke being given off. There's that carbon snake starting to form and all that heat being given off from this very, very exothermic reaction. Exothermic means a reaction that gives off lots of heat. And you can see just a ton of smoke being given off. We would only want to do this in a fume hood, right? Otherwise, it could be dangerous for us to breathe this in. And it's growing so tall that I'm going to try to pull out the shot a little bit. And you can see that it's growing into this really cool carbon snake. It's actually leaning towards us a little bit. So the version that you do on the 4th of July is not quite so dangerous, right? It doesn't have sulfuric acid. That reaction is initiated by the fire that you bring to the little disc, but kind of similar in process, making the carbon and having it grow into this snake-like shape. Pretty cool. I hope you all enjoyed this. Again, please don't try this one at home. This is a great one to enjoy on video, or when you're old enough, come to college and we can do it together. Here we have an exciting demo, not something you can try at home, but a pretty fun one, especially fun to watch in person or on video. So my two students have two different solutions that they're going to add to the speaker, and maybe we'll get to see something happen. So watch closely. Okay, well, it doesn't look like anything's happening. Maybe we should start stirring. Oh, it still doesn't look... Oh, look at that! It turned instantly blue. How cool is that? This is what we call the iodine clock reaction. It takes a little while before the reaction happens, and then it immediately turns jet black or dark blue. Now we're going to do the opposite. So we're going to treat it with some chemicals to take care of the waste. So my student is going to put the waste speaker up on the tray so you all can see it. And we're going to pour that black chemical back into the waste speaker, and it's going to basically reverse the reaction so it goes back to colorless. And again, this is called the iodine clock reaction. We mix two chemicals together, they make iodine, but it takes a while for the right amount to appear, and once we have the right amount, it makes this complex with the starch that looks immediately, instantly black. Really cool, really fun. Can't do it at home, but so fun to watch on video. We hope you enjoyed that one. Okay, we have a very interesting reaction for you today. I don't want to spoil the surprise. So the first thing I'm going to have my student do is add a second solution to the one that you already see in front of you. You can see that both of these solutions are clear, colorless liquids, but they obviously must contain something a little bit different. Otherwise, we would have had them together at the beginning. And so now we're going to add a third clear, colorless liquid to this mixture. And hopefully we'll get to see some stuff happening. Ooh, look at that. It's turning kind of an orange color right away. Oh, look what just happened. Instantly turned blue. How pretty is that? And so this is what we call the, oh, look what's happening. It went colorless. This is so, oh, look, it's turning orange again. Oh, and blue. So this is a very cool reaction called the oscillating reaction. And what's happening here is a reaction between iodine turning into different versions of itself. So sometimes the iodine is in what we call the molecular form, and that's what you see with the blue, but then sometimes the iodine is present in its ionic form, and that's what you see with the clear and the orange. And so it just continues to go back and forth as the reaction reacts it away and forms it again, and reacts it away and forms it again. It's basically two competing reactions going back and forth, back and forth. And then the blue that you're seeing is, again, from the iodine molecule complexing with a little bit of starch that we have present in the reaction. And so it makes this really dark color, but eventually that gets reacted away, and that's when we go back to colorless and then slowly back to the orange again as more of the ionic iodine forms, and then the molecular forms, and we go instantly back to blue again. So again, this is an oscillating reaction, a very cool reaction. Not something you can try at home, but something that's very beautiful to watch on film, and maybe someday you can try it in a chemistry lab yourself. We hope you enjoyed it. Okay, this is an exciting demo for you all. This is called unicorn milk. In front of you, you see this purple solution. We actually have it on a stir plate. It's stirring it for us. The purple solution is actually a mixture of milk of magnesia, distilled water and something called universal indicator, which is an acid-base indicator that actually is a mixture of lots of different acid-base indicators, so it has the whole rainbow of colors as part of it. This purplish color means that the pH is pretty high. It's a basic solution. It's around pH 10. What we're going to do is we're going to add some acid to this, and we're going to change the pH to really, really low, and you should see the colors change. But then the really cool thing is that this mixture on the stir plate is actually a buffer, which means it wants to come back to its original color. So let's watch this happen. I'm going to have my student on the left add a splash of 1 molar hydrochloric acid. And there goes that cool color, but we see it get eaten up really fast, and now it's converted back to sort of a turquoise and slowly turning back into blue. And so we can see how that buffer is working to eat up that acid. So let's have him add another splash of that HCl. And there we go. So again, we get to that sort of lower pH color, but now it's going back to the higher pH. Let's add another splash. Oh, isn't that pretty? So again, why we call this unicorn milk, we're seeing all these pretty rainbows. I think we're going to switch to the stronger acid now. So this one is a 6 molar hydrochloric acid solution. We're going to add a splash of that, and we should see an even darker pink color up here. And add a little bit more. And so there we see some of that acid being eaten up, and we're going to add another splash. And there's some bright, pretty colors. Let's try some more. This is so pretty to see all these different colors happening. But again, remember what's happening. That strong acid is being eaten by this really strong buffer. Ooh, look at that pretty pink color, and again, getting reacted away. So let's add some more. Ooh, is that ever pretty? Look at all those rainbows. I love this demo so much. All right, let's keep going. What we're trying to do now is break the buffer. So that means adding so much acid that eventually the buffer is gone. It's reacted away. You can see that we now have succeeded in breaking the buffer. All of that milk and magnesia has been eaten up. It no longer has the power to convert it back to a high pH, and we're stuck at this low pH of this acid. We hope you enjoyed this demo. Not something you can try at home, only because you don't have the strong acids and you don't have the universal indicator. But you do have milk and magnesia, so you could try this with red cabbage juice and any acids you have in your house, like vinegar or lemon juice. Have fun. Okay, this is a very exciting demo for you all. This is called the Elephant's Toothpaste. Inside the 2-liter soda bottle you see in front of you is some 30% hydrogen peroxide, which is very dangerous, and you won't be able to find this in a store, so don't try to. But also we have some blue food dye and some dish soap. And now my student is going to add the magic ingredient, which is a catalyst called potassium iodide, and hopefully we'll get to see something really cool happen. So a catalyst is something that makes a reaction happen faster, and as you can see, it's starting to react with the hydrogen peroxide that's inside the bottle. The hydrogen peroxide gets broken down by the catalyst to make water and oxygen gas. The oxygen gas bubbles through the soap and makes a whole bunch of foam, and you can see it pouring out of the bottle like toothpaste, which is why this demo is called Elephant's Toothpaste, because it's really big. Perfect for elephants, right? Although it's not real toothpaste. And look at that beautiful blue color, and it just keeps pouring out of the bottle, and we get this really cool steaming effect that you can see because it's a very hot reaction. It's pretty cool. I hope you enjoyed this one. Again, this is called the Elephant's Toothpaste. Okay, we have a really exciting demo for you right now. We're going to do what's called the Elephant's Toothpaste. So in front of you, you see this tall graduated cylinder. In the bottom of the flask, we have some strong hydrogen peroxide. This is 30% hydrogen peroxide. You do not want to try this at home. You can't get this chemical for use at home anyway. And then we've mixed into that hydrogen peroxide some dish soap, and you can see we have drips of food coloring going down the various sides of this flask. And so we hope that this is going to give a really cool sort of a toothpastey look to it. So now my student's going to add the catalyst, which is potassium iodide solution. And as he pours that in, we should start to see it react. And whoa, look at it grow. That looks so awesome. That is some really cool Elephant's Toothpaste reaction. Look at all that foam. Look at all that steam. What a fun reaction. I hope you guys enjoyed that. Again, you can't try this one at home, but it certainly is fun to watch it on video. Okay, we have an exciting video for you. We're going to make what's called hot ice. This is actually a supersaturated solution of what's called sodium acetate. So I'm going to have my students quickly take off the lid and the paper towel that was protecting this, and we're going to immediately add what's called a seed crystal, and it should initiate crystallization inside the beaker. You can see the salt crystals growing. Look at that. And that's what we call hot ice. It instantly solidifies because there was so much dissolved in solution and it just couldn't handle that anymore. The seed crystal makes everything else crystallize. How cool is that? Okay, we're going to do another experiment with the hot ice. So in front of you, you see a watch glass with some seed crystals, and my student is going to very, very carefully pour the supersaturated solution onto these seed crystals in the hope of seeing something really cool happen. So a very careful pour, and we see the crystals start to crystallize. Even in the beaker, they start to crystallize. How cool is that? Right? This hot ice is just crazy. Not stable at all. You can see the crystals growing into the beaker. How cool is that? Right? So again, this is a supersaturated solution of sodium acetate. It immediately starts to crystallize when it touches a crystal of itself. Really fun, cool demo. Okay, for this demonstration, we're going to turn a copper penny into a silverish penny and then into a gold penny, kind of like the Olympic medals. So we're going to start by taking a regular penny that my student has holding up, and we're going to clean it by putting it in a little acid bath. This is a 1 molar hydrochloric acid solution. My other student is going to take a previously placed penny out of the beaker and show you how shiny it is. They're a little tricky. There we go. You can see that it's much shinier, a little bit more of that coppery orange color. And that's what an acid cleaned penny looks like. It gets rid of all that grime. And now we're going to put one of these acid cleaned pennies into this evaporating dish that we have over on the right. This dish contains a 6 molar sodium hydroxide solution along with some granular zinc. We have 3 pennies in there at the moment. Some of them have been in there for a little bit longer, and they're getting coated with a layer of zinc. And so if my student would like to pull one of these out, we can see how the zinc has coated the penny, and we've turned it from copper to looking a very shiny silver color. Isn't that cool? And so now we're going to give that one of these silver coated pennies a quick rinse with distilled water, kind of clean it off, get any of that solution that we were coating it with removed other than the zinc. And once we've got it rinsed a little bit, then we're going to turn this penny into the gold color, which we're actually turning it into the metal alloy brass. So the copper and the zinc combine through heat, and when they combine through the heat of this Bunsen burner, they will turn into the metal alloy brass, which has a gold color, kind of like brass instruments in a band. And so we just give it some time to heat, and eventually you'll start to see the gold color form, and we'll have changed a copper penny from copper to silver to gold. Oh, I think it's starting to work. Oh yeah, definitely. Let's hold that one up to the camera, and you can see that beautiful golden color. And we also have one other example on the bench top. And again, you can see all of the different pennies. So the first one is an uncleaned penny. The second one is an acid cleaned penny. The third one is a silver coated, it's zinc coated penny that looks silver. And the last one is the gold penny that's technically been transformed into the alloy brass. Not a demo you can try at home, but certainly something that's fun to watch on video, and maybe something you can try when you come to college. Hope you enjoyed it. Okay, we have a really exciting demo for you that you can try at home. This is the vinegar and baking soda volcano, but we've added a couple features to it. In front of you, you see a paper mache volcano, and so this is something you can make yourself to make your demo feel even more exciting as you do this in your kitchen. Inside of our volcano, we have a whole bunch of baking soda. So that's already been placed inside of it. And now my student is going to add the mixture of vinegar, water, and dish soap, and hopefully we'll get to see a lava flow. So as that vinegar reacts with that baking soda, it produces a ton of carbon dioxide gas, which mixes with all the soap and makes this really foamy liquid come out that looks, because of the red food dye, looks a little bit like lava. And it's so much fun to do this in a paper mache volcano because it makes it feel even more real. So we hope you have fun trying this one at home. Okay, we have another exciting demo for you that you can try at home. Inside of this bottle is vinegar, and we put a balloon on top of the bottle, and inside of the balloon is some baking soda. So when these two things react, we've already seen that this is going to produce carbon dioxide gas. The hope is it fills the balloon. So I'm going to have my student dump all the baking soda from the balloon into the bottle, and hopefully, like I said, oh, there it goes. It's starting to blow up that balloon. Very exciting, vigorous reaction. It's starting to even fill the balloon a little bit. You can hear the sizzling. And look at how big that balloon is getting. I keep having to zoom out just to make room for it. So this is something easy and fun that you can try at home, a different way to blow up a balloon using chemistry instead of just your breath. And all you need is vinegar, baking soda, a bottle, and a balloon. We hope you enjoyed that. Okay, we are going to do an experiment extracting DNA from strawberries. So in front of you, you see a bunch of mashed up strawberries. My student is going to add a mixture of salt and water and detergent to this, and this is going to allow us to extract the DNA from the strawberries. It has to be mashed up for a really long time, at least a full minute, if not two. So we're not going to do all of that on camera. We're just going to show you a little bit of the mashing right now, and then we'll come back for the next step. Okay, we've mashed it for a while, and now we're going to filter. We have to get rid of all the chunks, and we really just want the juice. So we're using a cheesecloth, and we have a funnel under it, and then we have a beaker under that. And so we're pouring all of this mashed up strawberry mixture into this funnel. Again, that has a cheesecloth on top of it, and we're going to use this like a filtering process. So you can see that the juice is starting to run through, but we're going to have to squeeze it a lot, and this is, again, kind of a lengthy process, so we're going to pause the video and come back in a second after we've filtered it properly. Okay, we're back, and we're going to pour the strawberry juice into this test tube, about half full, and now we're going to add some cold isopropyl alcohol. This is rubbing alcohol. And what happens is that the rubbing alcohol has a different polarity than the strawberry juice because that's mostly water and rubbing alcohol is mostly alcohol. And so what we see is the DNA start to separate out of the strawberry juice and kind of pull up into the isopropyl alcohol layer. And so you can sort of start to see it pulling out. Can you see that white chunk coming out? I'm going to try to zoom in a little bit. And we can see that white precipitate sort of pulling out of the strawberry. That is the DNA. It's pretty cool. So this is how it looks after a little bit of mixing, and you can see even more DNA being pulled up towards the top layer here. All the white and the bubbly stuff that you see is the DNA. There's a lot of DNA in strawberries, and so we get this really cool result. This is something you can try at home. Lots of recipes online, so we hope you have fun. A great demonstration, kind of a mixture of bio and chemistry. So biochemistry demo. Enjoy. Okay, I have another demo for you all that you can try at home. What we have on the right is a bowl full of homemade oobleck. This is simply a mixture of cornstarch and water, and then you can add food dye if you want to make it a color like we have here, kind of a bluish green. On the left, you actually see just regular old ketchup. These are both examples of what are called non-Newtonian fluids, which means they behave differently than most liquids do. And so we're going to look at some of their properties right now. So one of the things that you can do is just set a golf ball on top of each of these, and you'll notice that in the oobleck, it starts to sink pretty rapidly, but in the ketchup, it doesn't sink rapidly at all. And so even though they're both non-Newtonian fluids, they have different properties. The oobleck is actually going to behave more like a solid if we try to punch it, whereas the ketchup would never do that. So let's take the golf balls out and let's try punching the oobleck to show the difference in its properties. Like I said, with really fast force, it behaves like a solid. But if we slowly touch it it behaves like a liquid, which is really strange. We're not going to punch the ketchup because I think we all know that if we punched that ketchup, it would splatter everywhere. Now what we're going to do is we're going to drop the golf balls in more quickly. So like I said, we're going to drop them from a height with a little bit of force, and we see the difference. And so the golf ball on the right, it hit like a solid, but now it's slowly sinking in, whereas with the ketchup, it splashed and went all the way in. This is something you can try at home in your kitchen as long as your grown-ups let you get a little bit messy. It's really fun to play with this stuff and have a good time exploring the properties of non-Newtonian fluids. Okay, we have an exciting demo, actually 2 demos for you today. We're going to show you 2 different ways to make things in your home, kind of like slime, but one of them is actually a bouncy ball and the other one is slime. So we're going to start with the bouncy ball mixture. In this first cup, we actually have 2 tablespoons of warm water mixed with a ½ teaspoon of the borax, which is the box in the back. It's an old-fashioned laundry detergent. Mix those 2 things together and then add whatever your favorite food coloring is. My student's going to be adding some blue here. And so you want to mix that around until it's really well mixed and it has the color that you desire. Separately, you're going to measure out a tablespoon of glue. So you can see in the back we have the clear glue. You want to use that clear glue and not the white school glue. And then you're going to add some of this borax solution to the glue mixture. You can measure out about a ½ teaspoon, but really you just want to, a little bit, it doesn't need to be a lot, and add that to the glue. So once you mix those 2 things together, now you're going to add a tablespoon of cornstarch. And we're going to let that sit without stirring for 15 seconds. And after 15 seconds, then we'll start to stir it. So what we're doing in these 15 seconds is we're letting it react, right? Letting the things kind of come together, and then we're going to start to stir it. All right, so as we start to stir, you are going to be able to feel that it's eventually going to be almost impossible to stir these things together. So like my student is doing, just nice gentle stirs, trying to get everything to kind of incorporate together, but eventually it's going to be almost impossible to stir it. And so you can add little splashes of the borax solution if needed, but eventually you're going to want to pull it out of the cup and start to mold it into the shape of a ball with your hands. So I'm going to have my student start to work on that while I have my other student come in and show you how to make some slime. So to make slime, you need 4% polyvinyl alcohol solution that we've already made, and we've added some food dye to one of them in order to make it kind of a purpley blue color. And then in order to make this into the slime, we just have to add a little bit of that borax solution. So you just splash a little bit in, and then you start to stir, and you'll see that it kind of combines and starts to do what we call cross-linking. Oh, that looks really cool. And so it cross-links the molecules in the polyvinyl alcohol and makes them kind of gloopy, makes them stick together more. And so we get this really cool slimy effect. It looks fantastic, and it's a really fun slime that you can play with at home. You can put it in a Ziploc baggie and play with it later, and it's just so much fun to work with. All right, so I'm going to have my other student put her hands in front of the camera and kind of show where we're at with the bouncy ball. So we're working with that bouncy ball, trying to get it into kind of a ball shape and kind of squeeze some of any of the excess liquid out. And eventually we should be able to have it bounce a little bit. Still working, still trying to get it to have that right consistency. But these are really fun things that you can all try at home. We hope that you have the ingredients, and then you can make your own bouncy ball, or you can make your own slime. And there's lots of different slime recipes on the internet that you can look at for yourself too. Okay, and now we've let it go for about 2 or 3 minutes, and now we have a good bouncy ball that's going to bounce a little bit. Look at that. And the more you play with it, the more it'll bounce. And now we have the slime out of the cup, and you can see how it's squishy and stretchy and fun. And you can play with it and do all sorts of cool things, and it won't stain your hands because, you know, we've basically worked all of that into the slime itself. Anyway, we really hope that you enjoyed these 2 demos and that you try them at home and have fun making some chemistry experiments in your kitchen. Okay, this is an experiment you all can try at home. We're going to help you learn how to make slime or putty, whatever you like to call it. So in order to do this, you need some food dye, and then you need a mixture of glue and water. It's supposed to be a 50-50 mixture, so that means half of it is glue and half of it is water. And then you also need to make a 4% solution of borax. So borax is actually an old-fashioned laundry detergent. It's a white powder, and 4% solution just means 4% of the weight is from the borax and the rest of the weight comes from water. So just a little bit, like maybe 4 ounces of borax and then 96 ounces of water, but you don't have to make nearly that much. You can cut it way, way down, and your parents can help you with that math. Once you have those solutions made, you're going to pour a little bit of the glue mixture into a cup. Make the cup about half filled with the glue water mixture. So my student's going to do that for you now. So like I said, he's going to fill that cup about halfway with this glue water mixture. And by the way, this is just regular Elmer's school glue. Any kind of regular glue works great for this. And then pick your favorite color food dye and add however many drops you want to dye the glue, whatever color it is that you like. So a couple of drops, and then stir it up with a stir stick. We like to use popsicle sticks, and make sure it's really nice and mixed so it has exactly the color you want it to be. All right, once you're done mixing it and it looks beautiful, now you just add a couple splashes of your borax solution. The exact amount is not important, so just a splash or two, and then stir to see how it feels. And if it's starting to thicken up, that's the right idea. So it's starting to do what's called polymerization. So it's reacting with the chemicals in the glue and making them actually stick together more than they were sticking together before. I think we're going to add another splash. Try to thicken it up and do what we call cross-linking. So that's a chemistry term for the way that polymers react. Polymers are big, long molecules that have long chains, and cross-linking will link those chains together across the long chains. And once it gets nice and thick and real kind of slime putty-like, you can pull it out and play with it with your hands. So you can see that it looks kind of like putty or slime. And the more you play with it, the better the texture will be. It'll start to really feel like putty. Slime. It'll be a little messy at first, but with playing with it, a lot of that messiness will go away, and you can obviously just wash your hands right in your sink. And the other cool thing is that this is something you can store in a Ziploc bag and then pull it back out to play with it later. Everything that's left in the cup can be thrown away in the trash can, and that's how you can make your own putty to play with at home. We hope you liked this demo, and we hope you try it at home. So for this demo, you can actually try this one at home, and I really hope that you do. This is called a homemade lava lamp. So we have 2 examples in front of us, and we're going to make a new one as our 3rd example so you can see how to make it for yourself at home. So the bottle on the right currently contains just some water, and it's filled, not quite halfway. Then you can dye that water any color you want. So my student's going to add a little bit of food dye, turning it kind of red, swirling that around. Again, as much food dye as you want to make it the color that you want. Maybe a little bit more, make it a little darker, right? Yeah, that looks great. And then the other ingredient that you need for this is vegetable oil. Any kind of vegetable oil, and we all know that oil and water don't mix. So we're going to use a funnel to help us out, and we're going to slowly pour the vegetable oil into the bottle until the bottle is mostly full. Now, as you're pouring, you're going to see that the oil is going to try to mix with the water, and it's not going to do a great job, but it's going to be a little mixed up. And so you're going to want to spend some time just letting that sit so the oil and the water separate. That's why we have these other 2 bottles here that are already separated, because we made them ahead of time. To make the lava lamp action, all you have to do are add pieces of Alka-Seltzer tablets to your bottle. 1 or 2 pieces is all you need. And so we'll drop a half of Alka-Seltzer tablet into the green and blue bottles, and as you can see, they're starting to look like a lava lamp. So what's happening here is the Alka-Seltzer dissolves in the water at the bottom of the bottle and produces carbon dioxide gas. That gas wants to escape the bottles, and when it does so, it actually grabs globs of water on its way, and because the water is colored, we can see it in the oil that has just a tinge of yellow color to it. And so this is a really fun experiment that you can try at home. Remember, the blobs that you're seeing are the water not wanting to mix with the oil, because oil and water have very different chemical properties. The oil is what we call very nonpolar, the water is very polar, and so they don't like to mix. And again, the carbon dioxide from the Alka-Seltzer tablet is trying to escape the bottle, and that's why we see all these little blobs of water being pulled up into the oil from the carbon dioxide that's trying to escape. A great experiment for you to try at home. It's something you can do over and over again. Just add fresh Alka-Seltzer to the bottle every time you want to try it. And when you're done, seal up the bottles, but make sure it's done bubbling before you do that. All right, have fun with this one. Okay, we have a demonstration here that you can try at home. This is called the Rainbow Density Column. You need a bunch of different chemicals or things from your house really that have different densities, and you can layer them up in a tall glass. We're using a graduated cylinder. So on the bottom you see this beautiful honey with kind of an amber color. Now we're going to add some corn syrup that's been dyed green. And it is a little less dense than honey, but it's still a really thick liquid. We're going to pour that in down the side of the graduated cylinder. You can see how thick this liquid is, but because it's less dense than the honey, it's going to stay pretty much on top of the honey and make a nice layer between the amber color and the green color of this corn syrup. That green color just comes from food dye, so we can see the different layers really nicely. The next one that we're going to add is dish soap. Our dish soap is blue. It came that way from the store, but you could always dye your dish soap using some food dyes. And so again, a pretty thick liquid, but not quite as thick as the previous two. So a little less dense, and that means it's going to sit on top of the corn syrup layer. And so we're starting to see that third layer appear, and it looks really cool that we're getting all these different colors. The next is going to actually just be tap water, but we've dyed it red so you can see a stark difference between the layers that we've already performed. So the water is kind of our middle density liquid here. It has a density of what's called 1 gram per milliliter. The other ones were more dense than water, and then we're going to have a couple that come after water that are less dense than water. So you always want to have your most dense in the flask first, and then go lower and lower density as you go through your various liquids. The next one is vegetable oil, which we didn't dye at all. We just left it the color that it is. Vegetable oil kind of has a pale yellow color to it, and we know that it's less dense than water and therefore will float on the top of the water. And so we'll slowly start to see that layer up on top of the red water. And yep, you can start to see that kind of clearish, pale yellow layer of the vegetable oil start to appear. It looks really cool. And then we're going to do one layer after that. So the last layer is going to be rubbing alcohol that we've dyed orange with some food dye. And that's going to be our top layer of our density column. So you can see that my student's taking real care to do this nice and slowly by running the liquids down the side. You can use a pipette or a dropper if you need, and that helps a lot to make sure you're not going too fast. If you go too fast, they might accidentally mix, but if you go nice and slow, then they layer up on top of each other because they have different densities. And so that last layer, again, rubbing alcohol, dyed orange with food dye, and we get this really cool rainbow density column. I hope you try this at home. It's a really fun demo. Have fun. Okay, this demo is something you all can try at home. What you see are 3 different eggs. So you would need to get yourself 3 eggs, and then you would need to get yourself some vinegar. And my student put 1 egg in each cup with just vinegar for 2 days and placed those in the fridge. During those 2 days, the vinegar started to react with the shell of the egg and dissolve it away. You can see the result in the picture in the background. The shell is gone, and all we're left with is a raw egg with its membrane exposed. How cool is that? And then he very carefully used a slotted spoon to transfer the egg into the 3 green solutions that you see in front of you. The solution on the left is a solution of corn syrup dyed with food dye. The solution in the middle is distilled water with 1 tablespoon of corn syrup. And then the solution on the right is just distilled water. All 3 have a little bit of green food dye. You can choose to use any color you want. So when you put that raw egg without its shell into these 3 solutions for 1 day, you can see these weird results that you see in front of us. So the one in the middle is kind of like our control. There's not much change other than it turning into the green color from the food dye. We don't see the egg getting bigger or smaller. It stays pretty much the same size. But if you compare the one on the left and the one on the right, you can see the one on the left with the corn syrup is much smaller, and the one on the right with the distilled water is much bigger. So what's happening here is osmosis. We have a transfer of liquids through the membrane of the egg. In the corn syrup example, the water that's inside the egg pulls out and makes the egg shrink because something is being lost from inside that egg. Whereas with the distilled water, the water from the outside goes into the egg to make it bigger. And this is all thanks to osmosis. I hope this is a demo you'll try at home and learn a little bit more about osmosis and egg membranes. Okay, this is a demo that you can try at home. All you need is a dish tub or bread pan or something filled with water, and we have it filled about 1 inch high, that's all. And then you get to make yourself a little boat out of aluminum foil. And the most important part of the boat is that you have to have a little opening at the back end of it, because that's where we're going to add our special ingredient to power our aluminum foil boat. And so all we have to do to power this boat is put a little bit of dish soap right in that back opening. My student's going to drop it in now. Boom! Look at this boat go. So what happens is the soap spreads out on the surface of the water, and as it does so, it pushes the boat forward to make it look like it's going. The magic of basically soap and water not mixing very well at the beginning. Of course, you can make them mix later, but those soap molecules spread out on the surface of the water and push the boat forward. Really fun. You can do this over and over again as long as you clean out the dish pan and put in fresh water, because once the soap's in there, it's not really going to power it anymore. So have fun trying this one at home. Okay, this is another demo that you can try at home. We're going to make fast growing crystals. Now crystals never grow fast, but these will grow a lot faster than most. You can grow them in a couple of hours. You just need some Epsom salt like you see in front of you and some very hot water. You're going to pour a bunch of Epsom salt into that hot water to get it to dissolve. And we want to get to a point that's called saturation. That means no more salt will dissolve in the water. And so you kind of need a lot, and it's going to get, kind of, as you can see, almost thick, kind of cloudy, right? And if you can't get any more of the salt to dissolve, then you know you've reached, again, what's called the saturation point. Once you have enough of that dissolved, now you can add some food coloring, any color you like. Our students have chosen blue. Stir that in. So the salt and solution makes a beautiful color of whatever food dye you've chosen, and then pour that into a bowl. And then the easy thing is to just carefully transfer that bowl into your fridge to let it cool. The water will start to evaporate and the crystals will start to form like you see on the right. Now, depending on how long you have it in your fridge, you will get differently shaped crystals. So this is fun, easy. You should have crystals in a couple of hours, and I hope you all have fun trying this at home. Okay, we are going to attempt a demo that makes a cloud in a bottle. So right now we have a very hot flask of boiling water dyed blue with a flashlight shining on it. You might hear a rumbling in the background. That's our vacuum pump. My student's going to turn on the vacuum, and we should see a cloud instantly form inside. Let's see what happens. And look at that, you can see the cloud form inside the bottle. So what happens with the vacuum pump is that it removes the air that's on top, and then the boiling water wants to replace that, and so we immediately see this cloud form. That was pretty cool. Not exactly something you can try at home, although you can try it with balloons. Works better with a vacuum pump. We hope you enjoyed that demo. and tip over. Using a chemical called potassium iodate. Okay, hang on. So he's going to use a propane torch to do this, and so we're gonna. Okay, let me start over. All right, so let's turn the propane tank off, and I'm going to have my other student add the gummy bear, and hopefully we'll get to see something really exciting happen. I think that's enough with the melting, and so we're ready to add the peanut M&M. Oh shoot, what happened? Oh. And so it should form a cloud. Let's see what happens.
That didn't work.
Weird. Okay, we'll go with the first one.